All right. Advent of Code 2024, Day 14. Restroom Redoubt. One of the historians needs to use the bathroom. Fortunately, you know there's a bathroom near an unvisited location on their list, so you're all quickly teleported directly to the lobby of the Easter Bunny headquarters. Unfortunately, Easter Bunny headquarters seems to have improved bathroom security again after your last visit, which was 2016, Day 2. Wow. The area outside the bathroom is swarming with robots. To get the historian safely to the bathroom, you'll need a way to predict where the robots will be in the future. Fortunately, they all seem to be moving on the tile floor in predictable straight lines. Make a list of all the robots' current positions and velocities, one robot per line. For example, each robot's position is given as P equals XY, where X is a tile the robot is from is the left wall, and Y is the number of tiles from the top wall when viewed from above. Okay, so it's XY coordinates instead of row col. That's fine. We can work with that. And then we have a velocity. Okay, so got it. XY are given in the tiles per second. Positive X means the robot is moving to the right, and positive Y means the robot is moving down. So velocity of 1 and negative 2 means that each second the robot moves 1 tile to the right and 2 tiles up. Got it. What's outside the actual bathroom are in a space which is 101 tiles wide and 103 tiles tall when viewed from above. However, in this example, the robots are in a space which is only 11 by 7. Okay. The robots are good at navigating under each other due to a combination of springs, extendable legs, and quadcopters. So they share the same tile and don't interact with each other. Okay. That makes things easy. We don't have to worry about collisions. Visually, the number of robots in each tile in this example looks like this. Okay, so it's one robot in all these locations and 2 robots here. Understood. These robots have a unique feature for maximum bathroom security. They can teleport. Oh. When a robot would run into an edge of the space they're in, they instead teleport to the other side, effectively wrapping around the edges. Okay. All right, we can write a quick little test for that guy. Right. Here's what robot with this velocity does, or position and velocity does, and we can see it goes up, and then it wraps around from the bottom. And it wraps around to here. All right. The historian can't wait much longer, so you don't have to simulate the robots for very long. Where will the robots be after 100 seconds? In the above example, the number of robots on each tile after 100 seconds has elapsed look like this. To determine the safest area, count the number of robots in each quadrant after 100 seconds. Robots that are exactly in the middle, horizontally or vertically, don't count as being in any quadrant. Oh, okay. So the only relevant robots are these guys. All right, so we took this guy out of the picture because, literally, we took him out of the picture because he's exactly in a row or column. And these two as well are gone. Okay. In this example, the quadrants contain 1, 3, 4, and 1 robot. Multiplying these together gives a total safety factor of 12. All right, this doesn't sound bad at all. Wrapping, we can do pretty easily with just a mod operation, right? The way mod works, right, is -1. So this is the XY coordinates. So we know that it's how many tall? 103 tall. So -1 mod 103 is 102. So we just add 102. And that gives us our position. We don't have to worry about wrapping. I'm assuming that the numbers are all within reason. Let's take a look. Get input 2024 day 14. There's 500 robots. And these numbers all look pretty reasonable. Let's see are there any that are outliers? I don't see any with a quick visual scan here. They're all less than 100 in magnitude. I saw 96 here. But they all, oh no, here's one that's 102. All right. But all on that order, right? I see 100, 102 here. But they're all pretty, oh, I see. They're all less than the mod. Okay. This one's 100, so okay. Perfect. I mean, that's good. That's good. That makes it pretty easy, I think. Let's set this up. Um, 26 down. Day 14 in here. Bake and run. 24. I try to remember to do this before I start the solving part, but every so often I forget. Okay, so we can create a robot struct with a position and a velocity. And we can impl from stir for robot. And it's fairly straightforward. Let's write a little test to make sure we're implementing from stir correctly. Test parsing. So I should be able to say let robot, oops, equals, and then we can just grab this guy. Where was the singleton guy? Right here. Copy. So we do that, parse, unwrap, and then we can just assert EQ. Our position is 2, 4. And we can assert that our velocity is 2, -3. Right? And if we hit test and save, it should fail. Oh, I haven't finished writing this. Yeah, we got not yet implemented. So how do we want to do this? I mean, a regex would work great, but I don't want to pull in a regex package. So let's say let PV is equal to s.split once on space V equals. And then the velocity is on V. P we have to break down a little further. Is P dot split once on equals. Unwrap. Okay, so now we have P and V. Let's write a little function, get XY, which returns an I64. So this is going to be let XY equals S split on comma, split once on comma. And then we're going to return X parse unwrap, comma Y parse unwrap. Right? That compiles, yes. Well, except for that part of it. Okay, and now we're going to say, okay, self position is get XY of P, and velocity is get XY of V. Oh, velocity. My brain is so used to typing vec that I typed vec again. Okay, and the test works, so that means that we actually have, we're parsing correctly. So now the parser is just, well, let's grab here, robots, vec of robot. The parser is let data equals AOC lib read lines from input. Oops. And then let self robots equals data split. No, data. Yeah, these are lines. Lines iter map robot parse unwrap. And we should be able to just print them all out. Self robot. Oh, I have to give it debug. Robots. Oops. Oh, I forgot to do the collect. And then over here we'll hit run, and we get all the robots. So the first one is 4073. Negative 9664, correct. And the last one is 4170, 3921. Perfect. Okay. So we got everything. Everything's good. And now let's write, I don't know, a tick function, because it's every second, right? We're going to move once a second and change the position of each robot. We'll need a for loop for that, but let's just write a single robot tick. We can do this. Can I do it this way? Oops. Test 1 tick. So we'll grab this robot. We'll make it mutable so we can modify the positions. So we'll say robot tick. And then we're going to assert the position is going to be after 2 seconds. The x coordinate is 1, 2, 3, 4, 5, 6, which makes sense because we're adding. Oh, no, it doesn't. Yeah, after 1 second. Here we go. Because we're going to add 2 and 2, we'll get 4. We'll add 4 and negative 3 and get 1. And then a robot pause. So that should work. Well, I mean, that should compile once we create a tick method. And we got a to do. This does not return anything. There we go. If we hit test, it should say not yet implemented. Good. And then tick is very easy. We're going to make it a mutable reference to self. We're going to say self pause 0 plus equals vel self vel 0. And 1 is plus equals 1. And that test passes. Okay, so let's just test wrapping now. Because now this doesn't wrap yet. But after 2 seconds, we should wrap off the top, right? So let's do another. Let's test wrapping. So we're going to do 2 ticks, and it should wrap around the bottom, right? So this should be 6, and 1 minus 3. It looks like it's on the y coordinate. It's 1, 2, 3, 4, 5. That makes sense. All right, this should fail, right? And now we just need to do the mod. Oh, right. We don't know. The robot doesn't know how big the area is. We don't have that information stored there. So I guess we can store it this way. We'll just pass it in every time. It's a little annoying, but maybe I can come up with a better way to do it later. So this is self pause 0 plus this plus the width, mod the width. And then this is self pause 1 plus self vel 1 plus height, mod height. And that should fix that bug. Oh, it didn't work because, of course, all my calls to tick don't have the width and the height. Oh, right. Right. This is 11.7. That's why I parameterized it, because I was about to put 103 or whatever. Okay. So now that wraps. Okay. So I think we're ready. We've got everything we need to run this 100 loops. This is a pretty straightforward day 0. Part 1 for day 14 is pretty straightforward. So we just for each robot in self robots iter mute robot tick, which was the width. The width was 101. Yeah. 101 wide and 103 high. And then we just, oh, yeah, and then we have to figure out the quadrant business. Let's grab the test input, as one does. So we're going to say test quadrant. And I'll make a little function here. Does that make sense? Yeah, this makes sense. Fn. And we just need to add up all of the, or we need to multiply the count of each. I'm going to separate it out into a multiply step and a summing step. So we'll do the summing step first. Self. Oh, here's where we need to know the width and the height. Self width equals 103. Self height equals 101. Is that right? Or did I have that backwards? I have that backwards. Self width, self height. Okay, it's a little sloppy, but okay, it's gonna work. It's gonna work. We're gonna return use size 4. Oops. Let counts equals 0 use size 4, and then we're going to just return counts. So this is going to loop over all the robots. We're going to figure out the position, which quadrant we're in. How do we want to do that? Oh, I know how to do it. Okay, let x equals robot pause 0 compared with self width over 2, and let y is equal to robot pause 1 compared with self height over 2. And we're going to ignore anything that's equal to the width and height. Yeah, so we can do is match, watch this, match XY. And fill in match arms. Let's clean that up a little bit. Anything with an equal we don't care about. So it should be 4 after we're done. Yep, and then we don't, if let some quadrant equals this, and this will be sum 1. It doesn't matter which quadrants they're in, right? Sum 2. We just need to get the 4 values. Sum 3 and sum 4. This is going to be none for everything else. And then, oh, no. If this is equal to this, so now we know which quadrant the robot's in. We just need to increment the count for that. Counts quadrant plus equals 1, and we just return the count. Expected, plus equals 1. There we go. Okay, let's see if that builds. Quadrants is never used. I know that. Let's run the test here. We have let lines is equal to, and I think I still have this in my paste buffer. I do. So we'll add quotes, quote dot to string. Oh, it doesn't matter, right? We don't need to do that. Oops, I forgot the comma. Because we can just parse it out this way. Oh, I meant to do that. There we go. So now we can grab all the robots and calculate the quadrants. Let mut robots equals vec new for line in lines. Robots push line parse robot unwrap. Okay, so now we have all the robots. We're now going to run for 100 seconds for robot in. I'm just re-implementing part 1, aren't I? Iter mute robot tick 11 by 7 So we've done this, and now we're going to get the quadrants. Let quads equals. Oh, yeah, that's what I should have done, right? Let's do it this way. Let mut AOC equals AOC 2024 14 default. And then we can do is this AOC robots, right? And then we should be able to let's do a step here, and which goes for robot in robots iter mute robot. Yeah, robot dot tick self width self height, right? And now we can just call step once we set up the AOC width is equal to 11, AOC height is equal to 7. We should be able to say AOC step. And then this part here is quads is AOC quadrants. And then, right, U size 4. And then we should be able to say it's equal to 12, it says. So quads, iter, product, U size. How's that? All right, let's hit test. Oops, index is out of bounds. Len is 4, but the index is 4, and that's on line 37. Oh, right, this should be 0, 1, 2, 3. There we go. Oh, and that worked. So the quadrant code worked. All right, so I think we're all set for part 1. We just say self step, and then let quads equal self quadrants. And then we just put that product thing in here. Quads, iter, product, U size. Run. We got a big number. I'm not sure what I was expecting the number to be, but it's pretty big. We're multiplying 4 numbers with about 75 robots in each. Approximately? That seems big, but 75 to the 4th. Let me just do a calculator quickly here. Oh, it popped up on my other screen. 75 times 75 times 75 times 75 equals. So this is what 75 to the 4th is. 31 million. This is 218 million. Ooh, we might be over. Let's find out. No, it's the right answer. Oh, it's 125. I divided too many times. It's 125. All right, thank you, CodeMonk and Smab for the stars. Yeah, let me do this again. 125 raised to the 4th power equals. Yeah, okay. Now we're in the right ballpark. Yeah, I divided one too many times, and I got 75, and that's not even correct. It should be 62 and a half. So who knows what my brain was doing. Git status, git commit -am, no, git add source. Git commit -am 2024, day 14, part 1. That was relatively easy. I'm kind of worried about what part 2 might be. I mean, if it's do it a million times, then we just look for a loop, right? I'm sure there's a loop in there somewhere. But we've done one of those, haven't we? Oh, maybe we haven't done one yet this year. Okay, let's find out what part 2 is. During the bathroom break, someone notices that these robots seem awfully similar to the ones built and used at the North Pole. If they're the same type of robots, they should have a hard-coded Easter egg. Very rarely, most of the robots should arrange themselves into a picture of a tree. That's great. That is absolutely hilarious. That'll trick all the LLMs. They're not going to be able to solve that one. Was the fewest number of seconds that must elapse for the robots to display the Easter egg. That's cute that it's an Easter egg and we're in Easter Bunny headquarters, but it's a North Pole robot. So the North Pole robot has an Easter egg, which is their mortal enemy, but it's a Christmas tree. That'll stick it to them. Oh, John, thank you for the star as well. Smab says part 2 is fun as well. The code monk gives me a Christmas tree. Thank you. All right. How are we going to do this? Let's just print out. Let's make a little robot printer. I'm not storing them in a way that make it easy to print, but we could do it this way. FN display self. And this will just dump it out. Or maybe I should implement display for AOC. Yeah. Let's do it up here. Impl display for AOC 2024-14. What we'll do is we'll say let mut floor is hash set new for robot robot in self robots floor dot insert, because overlapping ones don't matter. Oh, maybe we could do it this way. We could say self robots iter map robot pause collect into a hash set. Can we do that? And that's the floor. And now we're going to say for y in 0 dot self width height. I'm so used to row call. For x in 0 dot self width, if floor contains xy. Oh, we can just say print. No, right bang f comma this thing. If floor contains, then we're going to put a hash. Else we're going to put a dot. Question mark semicolon. And then rightlen f. And then OK. It almost compiles. We have to pull in hash set, and apparently I use a lowercase c here. Yeah. Let's display this version of it after 100 loops. Let's go to part 2. Self-display. Oh, print lin. Right. I forgot. Like this, self. Oh, we can just do it all at once. Self like that. There we go. Oh, and it's wide enough, but it's not tall enough. So this is after 100 seconds. So I think what I'm going to have to do is just loop. I'm going to assume that it's not in the first 100. Let mut seconds equals 100. So we've done 100 seconds already. So we'll say loop println after seconds println self, and then we're going to say self step, and we'll go back to the top. So this will end up being an infinite loop. And then what? Oh yes, self step seconds plus equals 1. I know this is unreachable. Let's say while seconds is less than 1,000,000. It's probably going to be less than 1,000,000 that we see a tree. So we're going to figure out how we're going to see a tree here. Cargo run less. Look for the word after, and that way we can watch the display change. Oh, that's interesting. Let's see what we got. Does it look like it's converging onto something? I apologize for the noisiness. I don't know how this is coming across on Twitch. I'm just looking for, do we look like we're seeing any pattern at all? Oh, that was interesting. It's kind of, everything is kind of down near the bottom. I wonder if that's, let's keep track of this. It's 175 seconds. Oops. We see something interesting. The other one was kind of more vertical. It had a verticality to it. So we'll see if we see any more of those things. I honestly don't. Oh, yeah, right there. Right? 204 as a vertical one. Let's separate these. So we have 204. This is a horizontal pattern and a vertical pattern. What else we got? Any other patterns showing up? Oh, yeah, here's another horizontal pattern at 278. I'm assuming there's going to be a vertical pattern next, because that's the way it's been working. Looks like it's been alternating. No? Oh yeah, right there, 305. Now that's interesting. This one's 103 and this one's 101. Okay, I think we're onto something. There might be like two different patterns here. So if we scan forward to 281 or 381. Ah, look at that. Okay. And then if we scan forward to 406. Yeah. Okay. I think we're onto something. I don't know what we're onto, but we're onto something. Maybe I just print out these. Starting at 175. But there was another one. Oh yeah, at 101 there was a pattern. Okay. How do we want to do this then? We'll say let hars pattern. Now this is just specific to my input, I'm sure. I'm sure different people have different patterns. But we'll just print out the pattern one. Let mod vert pattern equals 204. Okay. So if seconds equals horizontal pattern or seconds equals vertical pattern, then we're going to do this. And then I want to increment actually so this started at 103 then, right? And this started at 101. So we can just mod those, right? All right, we can just take a look that way. Yeah, they're not mutable. Okay, they don't need to be mutable. Let's run this. Oops, I meant to look for after. Yeah, there's the vertical pattern. Oh, I have this wrong. Oh, no. If it's a multiple of, right, 103. I assume the 103 was it, right? Yeah, here's 103 with the vertical pattern. If we divide, oh, I see. No, this is starting at 103, but it's going up by 101. And this is starting at, well, I'm guessing it started earlier than, this is going up by 103. Right, and this, I'm sure the pattern in here somewhere. We just got to figure out when to print out the values. This would have started earlier, right? This would have started at 72 or something like that. So let's start at 75. mod I'm going to shorten these up. 175. That's when we print the first one of those. And mod VP equals 103. Right? So if seconds is equal to HP or seconds is equal to VP, then we'll do that. If seconds equals HP plus equals 103, else VP plus equals 1. This, I was getting too tricky for myself. All right, so there's the vertical pattern. There's a horizontal pattern. Vertical, horizontal. Okay, we got it. So it's probably, seems like it's coming together, right? Actually, I don't know if it is. I mean, it's definitely something. If I get to like 20,000, then maybe we'll try a different approach. Although it does seem to be doing something here. What do you think? Am I on the right track? Oh, I was expecting the whole thing to be a Christmas tree. That's neat. All right, 6870. Let's see if that's right. Yay, that's the right answer. Okay. Let's check out the leaderboard. I want to see, yeah, I'm sure the LLMs, yeah, 12 seconds. This has to be LLM, right? I'm guessing probably the 1.5 to 2 minute point is where the humans are doing it.